Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We're excited to have three experts with us today on our webinar, Effects of Occupant Behavior and Air Conditioner Controls on Humidity in Typical and Low-Load Homes. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You can either listen through your computer or telephone. You can choose to listen through your computer. Please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, you should already see a box on the right that will display the phone number. Panelists, we ask that you please mute your audio device while you're not presenting. If you are having any technical difficulties with the webinar, you can contact the GoToWebinar's help desk for assistance. Throughout our webinar today, you can ask questions through the question pane. Please use that questions pane and just type in your question at any time. If you are having difficulty viewing the materials through the webinar portal, we will be posting PDF copies of the presentation on the Building America website. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we'll have a question and answer session and closing remarks. For more than 20 years, the DOE Building America program has been partnering with industry to bring cutting-edge innovations and resources to market. This Building America webinar will provide an overview of research that's being done at the National Renewable Energy Laboratory and Oak Ridge National Laboratory. And now for today's presentation. Our webinar is Building America, Effective Occupant Behavior and Air Conditioner Controls on Humidity in Typical and Low-Load Homes. Our panelists today are John Winkler and Jason Wood with the National Renewable Energy Laboratory and Jeff Munk with Oak Ridge National Laboratory. John is a senior engineer and his research focuses on residential HVAC systems, residential dehumidification control, and energy modeling tools. Jason is also a senior engineer in the Building Energy Sciences group. His research focuses on design, analysis, and experiments of heat and mass transfer devices and processes, primarily for HVAC. Jeff is a researcher in the Building Envelope and Urban Systems Research Group. His research has focused on laboratory and field evaluation of advanced HVAC and water heating equipment and buildings-to-grid technologies. I'd like to welcome John to start today's webinar.
Good afternoon, everyone. Thanks for joining us today. As the title of our presentation would suggest, our study from last year, which concluded in around September, focused mostly on the occupant impacts on loads in typical and high efficiency homes. And one of the main motivations for our study is due to the fact that the importance of loads is changing. And so this drawing here, which shows building efficiency on the x-axis and thermal load on the y, is showing how as we increase insulation and incorporate better windows, better ductwork, that the envelope loads are decreasing quite substantially as we improve building efficiency. As well as infiltration becomes a less of an impact, but at some point we need to add ventilation. The one load here that we see that is relatively constant and independent of building efficiency are the internal gains, which are starting to deserve more and more attention. To put it in a similar way, not only are the relative importance of the loads are changing, but the breakdown between sensible and latent is changing as well. And so the plot there on the left shows two house construction types, an IECC 2009 home and also an Energy Star version 3 compliant home, and showing the sensible load as a function of the outdoor dry bulb temperature. And you can see due to the efficiency measures in the Energy Star home, the sensible cooling load has been reduced quite substantially. However, on the plot on the right, we see how latent load, now a function of the outdoor dew point temperature, is relatively similar between the two homes. So this means that the ratio of the sensible and the latent loads is changing quite a bit as we improve the building envelope. As I'm sure many of you are familiar with residential buildings, the breakdown of latent and sensible cooling loads is quite complicated, and there's a lot of different interaction between the loads. And so here is a simple schematic showing the different types of loads that are present in buildings in the context of what our study particularly focused on. So you have envelope loads, which are, wall insulation, windows, and those are primarily, or I should say all sensible heat transfer, indicated by the red dot and the red line on the drawing. You have infiltration and ventilation loads, and there's both a sensible and a latent component to that. Level of furnishings comes into play with heat transfer into and out of materials. This would be thermal mass, but also the absorption and desorption of moisture into those materials, the buffering of moisture for the humidity inside the space. You have the air conditioner, which is the primary mechanism in most homes for moving both sensible and latent load. And the three aspects that we investigated are the blower off delay, so that's the amount of time that the fan runs after the compressor shuts off, the air conditioner sizing, and also the indoor airflow rate. Obviously, the occupants are a main contributor to the sensible and latent loads, both through internal gains. So this would be, occupants themselves, but also appliances, cooking and bathing and things like that. Window shading, so how much of the solar gain through windows is mitigated through drapes or blinds or shades, and also the cooling set point. So I don't think I really need to spend too much time to talk about how internal moisture gains are highly variable. And so this is a plot that we took from a paper a few years ago by Sam Glass, looking at the variability in measured internal gains, and those are indicated by the different points on this plot as a function of the number of occupants. And so even if you look at, just say, 3 occupants for the various studies that were included here, they measured anywhere between 5 kilograms per day of moisture up to around 20. And so that's quite a large variation. And so if you want to try to understand humidity loads in homes, you need to do so in the context of understanding how those are going to vary due to occupant behavior. So there are really 3 objectives to our study that we're going to focus on today. The first is looking at the sensible and latent cooling loads in a typical new construction home and also a low load home. And then we're evaluating the sensitivity of indoor humidity to variations due to occupants, such as internal loads, window shading, and air conditioner cooling set point. And then we're also going to investigate how certain controls of the air conditioner impact humidity, and what kind of guidance can we provide to installers and technicians to design the equipment and set up the equipment to mitigate potential humidity issues. So our approach was to utilize the Energy Plus simulation engine with stochastic related inputs to model the internal gains and the window shading. And so here is an outline of our talk. We're first going to spend quite a bit of time talking about the modeling approach and assumptions. We'll talk about the house input, the moisture buffering model, the air conditioner model, and then get into the stochastic approach to occupant behavior. We're then going to open it up to some brief Q&A, and at that point, we'd like for the questions to focus on the modeling approach to make sure that we're not leaving anyone behind and that we're not confusing in how we describe our approach. We'll then go through the results and wrap up with some conclusions, and then devote the rest of the hour and a half to additional Q&A. So I'm going to bring up this diagram again, and we're going to use this diagram to kind of walk through the different aspects of the model. First, we're going to talk about the envelope assumptions and infiltration and ventilation. So our study used a single house geometry with a single family home, 2,500 square foot, 3-bed and 2-bath. And this was based on data collected from the US Census Bureau. And we're primarily interested in simulating new construction homes. So neighbors were included 15 feet to the left and right, which is fairly common for a new construction development. We simulated 2 house types, one based on IECC 2009 construction, which we're calling the IECC 2009 home, and the other a low load home, which was a high efficiency home based on DOE Zero Energy Ready home requirements. On the next slide, I'm going to show what the construction inputs were for those 2 homes, but there were 2 major differences, I'd say, that should be pointed out here. One, the Zero Energy Ready home had ducts located in conditioned space, whereas the IECC home had ducts located in various zones depending on the Building America house simulation protocols with the house foundation type. And the other was the ICC 2009 home did not have whole house mechanical ventilation, whereas the low load home was ventilated to ASHRAE 62.2 2013 requirements. We looked at 10 different climates within the US, and it's kind of hard to see on the plot there, or the diagram there on the lower left, but we looked at Miami, Orlando, Atlanta, Nashville, Indianapolis in the humid climate zone, and then Albuquerque, Phoenix, Las Vegas, Denver in the dry climate zone, and we looked at one cold climate city of Minneapolis. So here we see just two tables highlighting some of the key construction inputs for the two house types. The top table up there is for the ICC 2009 home, whereas the bottom table is for the low load home. And per both of those requirements, construction practices change with climate zone, and so you can see how that's broken down here as well. The wall and ceiling insulation values are fairly straightforward. The ACH 50 values for the ICC home, that's there we relied on the DOE code field study results to determine those inputs. And like I said before, one of the major differences were the duct locations. And so that top table for the ICC home shows you what type of foundation types those homes had, where the homes in climate zones 1 through 3 were primarily slab on grade. The Nashville home had a crawl space, and then the Indianapolis, Denver, and Minneapolis homes had basements. In the ICC home, we did include spot ventilation, and we'll explain in some of the next few slides how we determined what those rates were, or how those were operated. And like I said, the low load home did include ASHRAE 62.2 ventilation, and we assumed a whole house exhaust fan running continuously for the year. So now I'm going to hand it over to Jason. He's going to talk a little bit about the EMPD model.
Thanks, John. So I'm going to focus primarily on the mass transfer part of the furnishings as opposed to the thermal capacitance part. I think we've had thermal capacitance in our building models for a long time, but we're trying to improve some of the moisture buffering models. So I want to start with a brief tangent to talk about NREL's research in moisture buffering and kind of the field tests we've done in that space to show that our models are based on experimental data. What I'm showing here is an experimental method we use to measure the moisture added and removed from a house. And the way we did that is we put a tank on a scale and we weighed the change in mass of that tank as we added or removed humidity. The plot at the right shows the profile we used. So we're adding a lot of moisture and removing a lot of moisture to get a square wave type profile of relative humidity. So we went to 65% relative humidity for 12 hours, and then we remove moisture to get down to 35% relative humidity for 12 hours. This gives us a large signal to measure the effects of moisture buffering. This shows that the experimental setup, which is the 5 pound per hour humidifier. There's also 150 pints per hour dehumidifier, not shown here on the screen. This is what we used. This allowed us to get to that square wave profile I showed before. So here are some of the results from one of the houses we looked at, where it actually was an interesting house because it was a house in Florida at a FSEC campus, and it started as an empty house where it had no internal walls and no furnishings. And so we were able to run several experiments and kind of just try to get a feel for what in the house, what parts of the house absorb moisture. And so the black line at the bottom shows the empty house, which really just shows moisture buffering from the exterior walls in the house. And in that case, we had a vapor barrier covering the slab. And then incrementally, we changed the experiment we ran. So on the y-axis here is showing how much moisture was absorbed cumulatively over those different 24-hour tests. And so the next test, we removed the vapor barrier to see the effect of the slab, which, as you can see, added another 2 kilograms or so of moisture absorption. And then we also added carpet, and then we added furniture and interior walls. And this really gives you an idea about how much moisture, 7 kilograms is 7 liters of moisture that can be added or can be buffered in the house due to the materials. In parallel, we were developing a model, and as John mentioned earlier, it's called the EMPD model, or effective moisture penetration depth model. It's a 2-layer model. So we have a surface layer that accounts for short-term buffering or high-frequency moisture loads. and a deep layer that accounts for longer term, on the order of a week or a few weeks, pretty much changes in the weather. And this model was implemented into Energy Plus. It's not a model we invented, but borrowed from someone else that had developed and implemented into Energy Plus. And it's a model that allows you to not have to do the detailed finite difference approach that had been used before, but solves much more quickly as long as you give it a good set of inputs. And so what we did was we took a lot of data from field tests that have been done over the years, some in Indiana, some in California, and some in Florida. And it also includes houses that have basements or crawl spaces or slabs, and some would have exterior foam insulation and some that don't. So a wide variety of houses. In fact, the one on the bottom right is a concrete block construction. We tried to understand how the different house constructions and climates impact the inputs. This is showing the data from the house in Fort Wayne, and you can see the EMPD model on the right shows a pretty good match between the data, which is the black dashed line, and the model, which is the blue line, compared to what's usually used in a building model called the effective capacitance model, where you simply take a multiplier on the zone air capacitance. It doesn't do a very good job of predicting internal moisture. And we realize this model is not perfect, but it certainly does a better job of predicting real moisture profiles compared to, or real relative humidity profiles compared to the old models. This table then is showing the inputs for our model. So we certainly have material property inputs. This is just showing the area inputs for the different materials. So what we did was we picked drywall, carpet, furnishings, as well as wood to account for the moisture buffering of the home. And the middle column there shows the inputs that were based on the field measurements, and then we kind of assumed a lower house, which maybe has a more open floor plan and less furnishings, and a high buffering case, which maybe has lots and lots of furnishings, and maybe more walls, more interior walls, to account for different levels of moisture buffering. And we'll talk about that in the results section later. So here I'm going to turn it over to Jeff from ORNL, and he's going to talk about the two other methods pieces of this presentation, and then we'll again take short questions at that point.
Okay, thanks, Jason. Yeah, so I'm going to talk about the air conditioner, I guess the equipment, HVAC equipment in each home, and the different parameters that we varied for our study. So starting off, we've got a table of the efficiency of equipment that was used in each city. The IECC 2009 homes used the regional code minimum efficiency equipment, and on the low load homes we used the zero energy ready home efficiency requirements. In locations that used heat pumps, we selected equipment from BIOP's default library that met both the minimum heating and cooling efficiency requirements. So we don't have any odd combinations of high SEER, low HSPF equipment in any of the climate zones. So in the study, we looked at three different design or setup parameters for the space conditioning equipment. The first is the equipment sizing, second is the blower airflow rate, and the third is the blower off delay. So our baseline for the equipment sizing was based on a ACCA manual J calculation. So that served as our baseline equipment size, and then we also looked at equipment that was twice that size to see the impact of oversizing equipment. The reason we're interested in oversized equipment as it relates to indoor humidity is that the oversized equipment will have increased cycling, which reduces efficiency and also increases latent degradation associated with the blower off delay, which I'll talk about in a few slides. Also, the reduced runtime of oversized equipment can decrease duct conduction losses, which is important when the ducts are located in unconditioned space. Moving on to the blower airflow rate, we looked at 3 different levels of supply airflow rates between 350 and 450 CFM per ton. To illustrate its impact or potential impact on humidity, I pulled some manufacturer's data on an air conditioner and plotted the cooling capacity versus the nominal CFM per ton on the x-axis. And so you can see as you move from left to right on the plot, the total cooling capacity doesn't change very much, the blue line, and the sensible capacity increases, shown with the orange line, and then therefore the latent capacity is decreasing as you increase the airflow. And so that results in a increasing sensible heat ratio, which is just the sensible cooling capacity divided by the total cooling capacity. So at 350 CFM per ton, the SHR is around 0.75, and as the supply airflow is increased to 450 CFM per ton, the SHR goes up to 0.83. Lastly, we looked at the blower off delay, which John mentioned was the time at the end of a cooling cycle after the compressor is shut off, but the indoor blower is still running. So typically, that's in the 45-second to 90-second range for air conditioners. So we looked at 3 values there, no blower off delay, 45 seconds and 90 seconds. And we also looked at the case where a homeowner may be running a continuous fan. So that's where the fan runs without stopping during the off cycle. And so the reason we're interested in this is that at the end of a cooling cycle, there's still a lot of condensed moisture on the evaporator coil. And so when the cooling stops and you continue to blow air over that coil, you basically get an evaporative cooling effect where you're evaporating that moisture back into the air. And so that's adding latent gain back into the house. And it also provides some sensible cooling due to the evaporative effect. So when we look to model these different parameters, the sizing and supply airflow rate are pretty easy to implement in Energy Plus. The blower off delay is not natively supported though. And so in order to capture the effect of the blower off delay, we used the energy management system program within Energy Plus, and used a latent degradation model that was developed in an FSEC report shown to the right. So the EMS program would calculate the additional latent gain and sensible cooling that would need to be added back into the living zone at the end of each time step to account for the blower off delay evaporation. And we also included a very small airflow rate during the off cycle, 0.1% of the on cycle airflow to account for natural convection or evaporation, diffusion that would occur as the coil is sitting there with a bunch of moisture on it. Okay, so switching gears to talk about the internal loads due to occupants and their behavior. As John mentioned, the number of occupants and their behavior can have a large effect on the latent and sensible internal gains. So in order to capture that, we wanted to avoid just using a single kind of national average profile, because that may work great if you're an average household, but for all the other homes that have more or less people or atypical behavior, it doesn't really provide that much insight into how the humidity is going to behave in their homes. So in order to solve this issue, we used this generation of indoor heat and moisture GIM tool that was developed at ORNL. So this was initially developed to generate indoor temperature and humidity profiles for evaluating moisture durability risks in building envelopes. And so I'm going to speak a little bit about it to make sure everyone understands how the internal load profiles were being generated. So if anybody's familiar with the Building America domestic hot water generator, this tool is kind of similar to that, where we're trying to generate realistic hourly profiles that are based on distributions of different statistical data. So on this slide, I'm going to walk everyone through kind of the flow of the GIM tool for the sensible and latent gains for occupants. So this is just specifically for sensible heat given off from humans and latent load due to perspiration, respiration. So the initial input into the tool is the house size and the number of bedrooms and bathrooms. And from that, we have distributions of the number of occupants from the residential energy consumption survey that allows the GIM tool to pick the number of occupants based on statistical distributions for the house size. Moving to the right, the GIM tool then decides whether the occupants are adults or children and their gender, and continuing to move on to the right, it develops a work schedule or a school schedule if necessary, if the occupants are employed, moving on to sleep schedules, all the way down until we've got an hourly profile for each occupant that tells us whether they're in the home or away, and if they're in the home, what activity they're doing. We then use the ASHRAE Fundamentals Handbook to pull average, sensible, and latent gains for specific activities. Those were mainly focused on office activities, but we tried to match those up with typical household activities. And then we have a range of metabolic rates for each occupant that provides variation that would be multiplied by those average, sensible, and latent gains. And so finally, we come up with a hourly profile for each occupant that gives us the sensible and latent heat generation for each hour of the year. And so we do similar things for cooking, bathing. There's distributions for different shower characteristics that account for how large the shower is, how frequently people do laundry. There's the different lighting efficiency in there, different appliances, and also the window shading is also determined by the GIM tool. So there's a lot of data that goes into this, and I've listed some of the sources that we've used on the left. We also supplemented it with some in-house experiments, and also there's some engineering judgment in there. We can't find data for everything, so at some point we had to make judgment calls. So each time the GIM tool runs, it makes a single profile So for this study, we ran it multiple times to come up with all these different unique profiles to provide us with variation in the internal loads. So we started out running 1,000 profiles to begin with, and in order to reduce our processing time, we down selected that to 200 profiles that gave a good representation of the larger set of 1,000. So this table shows kind of a summary of these internal load profiles, and we've broken them down by the number of occupants for each profile. So the percentages in the first column, those are coming from the RECS, Residential Energy Consumption Survey, that are specific to our house size. So in the first column, you can see the average latent load in pounds of moisture per day for the different occupant levels, and that did not vary between the IECC 2009 home and the low load home. And then the sensible loads are in the last two columns for the IECC and low load homes. The only difference in the sensible loads between the two house efficiencies is that the low load home included more efficient lighting and appliances. So they had identical latent load profiles, and the sensible load profiles just had the lighting and appliance sensible load reduced. So for reference, the Building America House Simulation Protocol loads for a 3-occupant house come out at 18 kilowatt hours a day for sensible, whereas our average for the IECC 2009 home is 16.3 kilowatt hours a day. So we've got slightly less sensible load. Part of that is due to the fact that the GIM tool allows for more efficient lighting to be used in the IECC 2009 homes. And then on the latent load, the house simulation protocol has 12.2 pounds per day for a 3-occupant house, and we are averaging 15.9 pounds a day. So over 25% more moisture from the GIM tool outputs. And part of that is due to the number of sources that we're trying to capture with the GIM tool. It covers a little bit wider range than the house simulation protocol. So we've got a slide here explaining box and whisker plots, which you'll be seeing a lot of. So at the end of this, you'll either love or hate box and whisker plots. But the median value, so that's kind of the middle point in the data set, is shown by the horizontal line inside of the box, with the box encompassing the middle 50% of data. So outside of the box above is 25% of the data, and outside of the box below is 25% of the data. The upper and lower whiskers would show the minimum and maximum values if there are not outliers, and the outliers are defined as being farther than 1.5 inner quartile, which is the inner 50% range, away from the lower quartile. So whiskers are basically representing the minimum and maximum values, except for when there are outliers. And we'll go through that again in this next slide here. So to try and illustrate the variation in internal gains and the different categories here, we've got box and whisker plots showing sensible and latent loads for all of the 200 profiles we used in the study. So if we focus in on humans here, for example, we've got a median value around 3.5 kilowatt hours a day for sensible load, and that's identical for both the ICC and the low load home, along with a slightly lower latent kilowatt hour a day. So the bars are in order for ICC sensible is first, low load sensible is second, and then latent is third. So some things to point out here is this category of bathing evaporation. So this is load due to evaporation off of towels or evaporation of moisture that's left inside like a shower enclosure or left inside a tub at the end of a shower. So for this category, we've got a negative sensible load that's due to evaporative cooling that's paired with a latent gain. So anywhere we had evaporation, we accounted for the negative, or I guess the sensible cooling associated with that. So as you can see, for the 1 to 6 occupants we looked at, we have a pretty large range in internal loads, both sensible and latent, due to the variation in occupant number and occupant behavior. Okay, so moving on to window shading. In order to model the window shading effect, we used a solar heat gain coefficient multiplier to reduce the amount of solar heat gain through the windows. We pulled our data for this from a DOE study that gave us the distribution and the number of window coverings per window, the different types of windows, and how common the different types of window coverings were. So based on that data, we ended up with a distribution shown here at the bottom left that ranges from 0.32 for the case with horizontal blinds, closed interior shutters, and exterior insect screens. So that was the largest amount of shading, up to windows where they only have exterior insect screens and no internal shading, up close to 0.9. Our median value was 0.71, which is very close to the Building America House Simulation Protocol year-round assumption of 0.7. So these values were selected per profile, and there were not any seasonal or daily variations. So it was assumed that the internal shading did not change throughout the year for any individual profile. Moving on to cooling set point. Originally, when we started this study, we had planned on treating the cooling set point as an occupant behavior, where we would vary that just like we would vary any of the internal loads. We would have a distribution of cooling set points and pick one from that distribution for each profile. The issue we had with that is that the cooling set point is not just an occupant preference, because people can adjust the set point in order to improve comfort. So if there's high humidity inside, a homeowner may reduce their cooling set point to try and make the house more comfortable. So we didn't feel it was going to be realistic to incorporate the cooling set point in with the rest of the things we looked at for occupant behavior. So instead of doing that, we just looked at it separately, picked a baseline value of 75F, and looked at a high and low value that were plus and minus 3 degrees Fahrenheit away from that 75 point. And just for perspective, the REX survey data has statistics on cooling set points, and so a 72 Fahrenheit set point was actually still pretty high. There were 46% of homes with a cooling set point below that, and the 78F still had 22% of homes with cooling set points above that. So our high and low values are still well within the range of common set points. And we used a constant heating set point of 70 degrees Fahrenheit for all of the homes. Okay, just to recap how the study was set up, we had two different efficiency level homes, the ICC 2009 and the low load home. We looked at 10 different cities in 6 climate regions and used 200 different internal gain profiles with those cities. And with our simulations, we looked at varying the moisture buffering, the thermostat set point, the blower airflow rate, the blower off delay, and the air conditioner sizing. All those simulations were run in Energy Plus, and we are interested in the sensible and latent cooling loads, the indoor humidity, and the cooling energy use for our outputs. The table on this slide kind of gives a summary of the different cases. So for each one of those boxes, we ran 4,000 simulations, so 2 cities, or 10 cities, 2 homes, and 200 different profiles. So that gives kind of an overall summary of the different cases we looked at. And this slide shows kind of the workflow through the computer side, where in BOpt we would generate the house models that would give us an XML file. The second step would be to run some modified Python scripts that would use the XML file and generate Energy Plus input files for all the different cases we're interested in. And then we would run all those Energy Plus simulations using the EP Launch utility to run a batch of files. Okay, so we're going to pause right now to answer any questions that are, I guess, pertaining to the modeling approach and assumptions.
Thanks, Jeff. So far, two questions have come in, so we'll quickly answer those and move on. The first question is regarding sizing. And so it says manual J allows for split systems to be upsized, and this is dependent on the type of air conditioner or heat pump, whether it's a single stage, 2-stage, or variable speed. So what we did we sized per manual, we calculated loads for manual J and sized equipment per manual S requirements that allowed us to upsize a little bit to try to meet sensible and latent cooling loads. And then to get the 2x factor, we simply just doubled that capacity. And so the 2x was applied to whatever oversizing was already done. And the second question was, did you model 2-speed or variable speed cooling to show the effect of control on humidity levels in the home? And the simple answer to that question is that no, we did not. So we didn't have variable speed air conditioners in our study. All the higher efficiency equipment was modeled using 2-stage equipment. And so those were modeled per how it's done in Energy Plus, where it picks the stage based on the sensible cooling load of the building and the sensible cooling of the two stages.
John, Jason, and Jeff, we had a few more questions come in, so either you can answer them now or at the end with our tail end Q&A. So would you like to continue, or would you like to answer a couple more questions?
Well, there's one other question about the moisture buffering. So there was the plot that showed the different amount of moisture absorption for the different materials. So we were measuring, that's how we measure the humidity. So we were measuring the humidity in the space, the relative humidity in the space with a TNRH sensor, so a capacitive resistance, or capacitive RH sensor. The scale was actually measuring the moisture transfer rate. So you would, since we accounted for all the moisture flows, we were able to measure the transfer in the materials by just subtracting whatever was left over after we took the amount absorbed versus, the amount of added versus the amount removed in any given time step or any given sample period. So yes, we measured the humidity, but the actual part about measuring the moisture in and out of the materials was based on the scale measurement. And we accounted for the fact that there was moisture being added or removed from the zone by measuring the relative humidity.
So there was also another question on how the low load home was ventilated, and that was with exhaust only ventilation, I believe. Correct me if I'm wrong, John or Jason.
I believe that's correct. It's possible that the cold climate cities did have an HRV per zero energy ready home requirements, but as we'll see on subsequent slides, that those homes didn't have humidity issues anyway. So all homes that were in the hot and humid climates did have continuous whole house exhaust fans. Okay, I guess we'll continue on to our results. And so, as Jeff pointed out, this is the box plot heavy section portion of the presentation. So kind of going in line with the objectives that I had originally presented, we're first going to talk about the sensible and latent cooling loads that were predicted in our simulations. And for this particular set of simulations, we included a whole house dehumidifier in the simulation to control the humidity, allowing us to estimate the latent load. And so for this section, we fixed the cooling set point at 75 degrees Fahrenheit and the RH set point at 55% RH. And there are really kind of two approaches to getting at the sensible and latent cooling load. One could sum up all the sensible and latent sources entering the building, such as through the walls, windows, infiltration, internal gains, ducts, etc. Or we could look at the capacity of the equipment on an hourly basis. And so we chose the latter for simplicity. And so those two equations there shown on the slide were used to calculate the hourly sensible and latent loads. The first equation is for sensible, and to calculate the sensible load in the building, we took the air conditioner sensible capacity, subtracted out the heat added by the dehumidifier and the power use of the blower to get at the sensible load of the building. Latent load was handled in a similar way. We looked at the latent capacity of the air conditioner and added that to the latent capacity of the dehumidifier to get the building latent load. We used these hourly calculations in two ways. One was to get at average daily peak loads on a monthly basis. And as you'll see on plots in the next section, we basically took the peak loads for every day of a given month and calculated the mean for a particular house. The next was just simply taking the average of the hourly sensible heat ratios to come up with a monthly mean. Okay, so let me take a second here to explain this plot we have here on the left. There's a lot of information conveyed here. So you'll notice that, first off, there are two main columns in the plot, and those columns correspond to house type. And so you have the IECC 2009 home in the left column and the low load home in the right column. Within each plot, there's a box and whisker corresponding to the month of the year, and that's ordered from January to December, and you can see the first letters of the month there at the very bottom. Each row in this group of subplots corresponds to the city. And so you see at the top, it starts with Miami in climate zone 1 and goes through Orlando, Atlanta, Nashville, and Indianapolis. And so here we're focusing on the climate zone 1 through 5 homes located in humid climates. And the values that are being plotted here are the average daily peak sensible cooling load. And so that's taking the peak sensible load for each day of a given month and calculating the mean. And the box and whisker variation are due to the 200 GIM profiles that were included in the study. And just to add some context, 20 watts per meter squared corresponds to about half a ton per 1,000 square feet, or for our house, 1.3 tons. And so you can see in the hotter climates, Miami and Orlando, this is a fairly typical sensible load in the summer months. And the reason it's quite a bit lower than what you might expect is because of the monthly average. This is not a design load. And so what you can conclude from this plot is that the sensible load was reduced about 16 to 25% by the efficiency measures used to go from the ICC home to the low load home. On this slide, we've added a plot. So the plot on the left is the same as the previous slide. That's the average daily peak sensible load. And now we've added the average daily peak latent cooling load on the right. And what you can see is that due to mechanical ventilation that is present in a low load home, there's quite a large increase in the latent load. And it's worth pointing out again that the set of internal latent load profiles used in the study were the same between the IECC 2009 home and the low load home. And again, to put this into context, about 10 watts per meter squared is approximately equal to 72 pints per day per 1,000 square foot, or 180 pints per day for our particular home, which is quite a substantial load that you can see that occurs in Miami and Orlando. So rather trying to add these two plots together in your head, on the next slide, we show the total cooling load. So that plot there on the left shows the average daily peak total cooling load, and the plot on the right shows the hourly average SHR. The load SHRs here are only shown for months that have a total cooling load greater than 1 watt per meter squared, and so that's why you see a lot of boxes missing from Atlanta, Nashville, and Indianapolis during the winter months. So in the plot on the left, you can see that the total load between the two homes is actually quite similar. And this is due to the increased latent load offsetting the sensible load reduction. For Miami, Orlando, Atlanta, and Nashville homes, the median summer load SHRs correspond to 0.71 to 0.8, which is pretty typical for conventional air conditioning equipment. However, in the low load home, the SHR was reduced quite a bit, and the median SHR ranged from 0.53 to 0.68, with the biggest reduction occurring in Orlando. And so this downward shift in building load SHR in the low load home is indicative that these homes will have higher humidity than the IECC 2009 home, all else being equal. And just for completeness here, this last slide showing loads shows for the other cities included in the study. So the dry cities of Phoenix, Las Vegas, Albuquerque, and Denver, and the cold climate city of Minneapolis. And here we show the average daily peak sensible cooling loads in the left plot and the average daily peak latent cooling loads in the right plot. And you can see that in the dry and cold cities, latent load still remains a fairly small fraction of the total load, and the total load does decrease in these cities shown here. Okay, so now we're going to shift gears a little bit and move away from sensible and latent cooling loads and talk about the humidity that we simulated in these homes. And prior to comparing the humidity in the homes, we first need to develop a metric. And so we naturally looked towards ASHRAE 55, which is thermal environmental conditions for human occupancy. And we took a fairly deep look at the evolution of the standard over time. And going back 35 years ago, ASHRAE 55 drew an upper limit on humidity at a dew point of 62.2 degrees Fahrenheit. And then they, about 10 years after that, moved to an upper limit based on RH, 60% RH, which is a fairly common metric used for Building America studies over the years and others. A few years later, they went to a wet bulb metric and then went back to a humidity metric of 62.2. And so they've kind of gone full circle, and that's kind of where it stands now today, is at the upper limit of 62.2, and at humidities above that number, ASHRAE 55 instructs users to evaluate the Fanger model to determine if a condition is too humid. And just to put some of these numbers into context, a dew point of 62.2 at a dry bulb temperature of 75 degrees Fahrenheit results in a roughly 64% RH, a little bit above the 60% metric. Whereas a 60-degree actually Fahrenheit wet bulb temperature corresponds to an RH of 70%, so that's pretty high. In addition to ASHRAE 55, we consulted the Humidity Control Design Guide for commercial and institutional buildings, and we also looked at the ASHRAE Guide for buildings in hot and humid climates, and both of these use dew points as metrics, 57 and 55 respectively. So for our study, we stuck with ASHRAE 55 and some of their guides and used a metric based on dew point. We picked a number of 60.2 degrees Fahrenheit, which is based on 60% RH at our baseline thermostat cooling set point. And then to aggregate the humidity numbers, we simply summed up the hours in which the indoor humidity was above that threshold. We didn't look at the magnitude of the excursion or the duration of the particular excursions. We simply summed up the hours over the given year. So here we show our baseline indoor humidity results. And just as a refresher, our baseline case had medium buffering, 75 degrees Fahrenheit cooling set point, 45-second blower off delay, and the blower airflow rate of 400 CFM per ton. And you see on the y-axis, we have hours above 15.7 degrees C dew point, which corresponds to 60.2. And then the cities go from climate zone 1 on the left over to climate zone 6 on the right, kind of alternating between humid and dry cities. So you can see that the IECC 2009 and low-load homes in the dry climates have nearly 0 hours that exceeded our dew point threshold. However, there are significant differences between the IECC 2009 home and the low-load home for Miami, Orlando, Atlanta, Nashville, and Indianapolis. And it's these cities that will really be the main focus of further analysis. The median hours above our dew point threshold in a low-load home definitely exceeded that of the IECC 2009 home. And this indicates that low-load homes of similar construction to the one in our study is likely to have higher humidity than standard construction homes. One thing that's important to note here is the variation in the box and whisker. And this variation is due to the occupant number and behavior and window shading, because all the construction characteristics of the weather for a given city were the same. And so you can see that even though the trend is for the median values to have higher humidity in the low-load home, there is quite a bit of overlap between the boxes for a given city. And so this indicates that occupant impacts can actually have a larger impact than the building characteristics in certain cases. So moving on to cooling energy. And so the cooling energy is determined by looking at the energy use of the outdoor unit as well as the indoor blower, which accounts for the additional energy consumed during the blower off delay period. And so this plot summarizes the energy savings of the low load home. The median cooling energy savings was 31 to 41% for homes in climate zones 1 through 4. And about half to 3/4 of that savings was due to sensible load reduction. And the remainder was due to the fact that the low load home had higher efficiency equipment. It's important to note also here that with the exception of Phoenix and Las Vegas, that there's the variation in internal loads due to occupancy and occupant behavior can have a larger impact on cooling energy use than the envelope and equipment efficiency improvements alone. And so this can be seen by the overlapping of the box and whisker. And it's important to note that this does not show the energy use of the gains themselves. This is only showing the energy use by the air conditioner required to reject the heat generated from the internal gains. So if you included the energy use by the gains, there'd be even a larger overlap between the two house types. Okay, so moving on to moisture buffering. So this shows, here we're showing a slightly different plot. The same quantities are being plotted. However, each box here represents the group of boxes shown by the different dashed lines surrounding the box and in the whisker correspond to different moisture buffering levels. And so you have low, medium, and high moisture buffering levels plotted for each house. And here you can see that at first glance, it would appear that moisture buffering helps the humidity in the home because we see the median decrease. However, in Orlando and in Miami, you see that the outliers actually increase the number of hours above 15.7 degrees C dew point. And the reason for that can be explained here. So on this slide, we're simply showing the impact of moisture buffering. And in these plots, we show two homes, one with high buffering indicated by the blue line and one with low buffering indicated by the green line. And buffering ultimately impacts the magnitude of the humidity fluctuations. So the arrows shown here are time spans during which the dew point threshold is exceeded. In the top plot, the mean dew point is 2 degrees C below the dew point. So in this case, higher buffering actually reduces the number of hours above the limit because it's preventing fluctuations above the threshold. In the bottom plot, the mean humidity in both homes is above the dew point limit. So in this case, buffering increases hours above the limit because it's preventing fluctuations below the threshold. And so that helps to explain some of the trends that we saw on the previous slide. Moving on to thermostat cooling set point. So in this plot, we're showing again the same homes as moisture buffering for the 3 different cooling set points investigated. We looked at 22.2 degrees C, 23.9, and 25.6. And these correspond to 72, 75, and 78 degrees Fahrenheit. So as we kind of expect, lowering the thermostat does reduce the dew point in homes because lowering the thermostat obviously results in additional air conditioner runtime, reducing the humidity. But we were kind of surprised by the order of magnitude here that we saw. So in the IECC 2009 home, we saw about a 90 to 100% reduction in the hours above the threshold, and in a low home, we saw between 80 and 96%. Obviously, this does lead to an increase in energy use, and that's plotted here. So this is annual cooling energy use versus cooling set point. And so we saw a median cooling energy increase between 27 and 44% when lowering the thermostat. So a pretty big increase in energy use. And just for comparison, because similar studies in the past have used RH as a metric, here we're showing hours above 60% RH versus cooling set point. And so the hours above 60% RH are reduced in most homes. However, the trend is reversed in the Nashville and Indianapolis low load homes, where the hours above 60% RH actually increases when lowering the set point. And so this is one of the drawbacks of using RH as a metric. And so that's why we included here to show the implications of different metrics. Okay, so now we're going to turn it on to Jeff to talk about results for the cooling system design and controls.
Okay, thanks, John. So I saw some questions come in regarding dehumidifiers, so I'm going to backtrack real quick just to cover those. So the only simulations where we ran with a dehumidifier were on these cases where we were trying to get the sensible and latent loads. So those were the only cases where we ran with a dehumidifier. On all of the results for the baseline case and moving on out, there was no dehumidifier included in the simulation. Hopefully that clears some things up. Okay, so moving on to the cooling system design and controls. The first thing we're going to look at here is the blower airflow rate. So as I mentioned before, we varied that between 350 and 450 CFM per ton. And you can see that the hours above the 60.2 dew point limit increased as the airflow rate increased. And there's a small to moderate impact on the change in hours. So then looking at the cooling energy associated with those changes, we didn't see a whole lot of variation, less than 1.5% change in the cooling energy use for adjusting that blower airflow rate. And so as you adjust the airflow, there's kind of a trade-off going on here. So as the airflow is increased, you're reducing your compressor power use, but you're also increasing your indoor blower power. So those kind of traded off, at least for the simulations and homes we used. Moving on to the blower off delay, we looked at the three cases. No blower off delay, 45-second blower off delay was our baseline, and then a 90-second blower off delay. So from this plot, you can see that the blower off delay had a larger impact on the hours above 60.2 dew point than the blower airflow rate, with pretty sizable reductions in the humid climates when you go to or when you eliminate the blower off delay. Seeing in the ICC home, when you go from a 45-second down to a 0-second blower off delay, there's pretty sizable reduction. And then looking at the cooling energy associated with that change, once again, we see very little impact on the cooling energy use between plus 1% and minus 2% for all cities that we looked at. One thing to note that our models did not account for thermal mass of the ductwork or the air handler. So in dry climates where you've got ducts in the attic maybe, and you're not concerned about humidity, then running that blower off delay could allow you to get a little extra cooling from the thermal mass of the ductwork and the air handler. And then we also ran the continuous fan case, which you can see increased our hours above the dew point limit significantly for all of the cities. So this is comparing no blower off delay to continuous fan. We've got huge increases in the Miami and Orlando cases. And so not only do you have increased humidity, but you've also got increased energy use due to running the indoor blower continuously. So based on that, we would say don't run in the continuous fan mode. And finally, looking at oversizing, there's a lot going on in these plots, but the first box and whisker for each city is our baseline case. So that's our manual J, manual S sized unit with a 45-second blower off delay and 400 CFM per ton. The second bar shows the impact of the 2 times oversize. So a cooling system that has twice the capacity of our baseline case. So for for all of the cities, we see an increase in the hours above the 60.2 Fahrenheit dew point threshold. And the increase is similar in magnitude to what we saw for going from a 400 CFM per ton airflow rate to a 450 CFM per ton airflow rate. So equipment size is not something you can readily change. Unfortunately, it requires purchasing a new unit. So we wanted to look at the case where, say a home has an oversized unit and has humidity issues. What could they do to help alleviate that issue? And so the third bar, or third box and whisker plot for each city, shows the oversized unit with the supply airflow rate reduced to 350 CFM per ton. So you can see for most of the cities that gets you back down to the baseline case roughly. So a pretty good decrease there. And we saw that the associated cooling energy use for that change is pretty small. And then the last box and whisker adds on eliminating the blower off delay. So oversized unit, no blower off delay, and back to 400 CFM per ton, sorry, not adding on to that, is an even larger reduction than for just reducing the airflow rate. So between those two things that can typically be adjusted without too much effort, some of the humidity effects associated with an oversized unit can be mitigated. So now we move on to the cooling energy use associated for all these cases. And once again, it's not affected that much, even by the oversized unit. And you can see that in the hot climates of Miami and Orlando, you actually see a reduction in cooling energy use for the oversized unit. And that is due to ducts being located in the attic and the reduced runtime of the oversized unit reduces the duct losses, and that outweighs the reduced efficiency due to cycling losses in those climates. And a few other studies have come to that same conclusion for homes with ducts located in unconditioned attics. So going through some of the conclusions from the load cases, we saw that the cooling load sensible heat ratios were below 0.6 for many of the summer months in the low load homes in humid climates. So comparing that to the typical sensible heat ratio of an air conditioner, which is usually in the range of 0.7 to 0.8, you can see that there's a mismatch there in the cooling load of the home and what the air conditioner can provide. So in order to make that up, then some supplemental dehumidification would be needed, or the homeowner would resort to adjusting the set point down. And kind of due to this changing cooling load SHR, additional research into separate sensible and latent cooling technologies may be advantageous as we increase home efficiency further. So we've established that the internal loads can have a significant impact on indoor humidity, and really the interface for comfort that most customers have now is that cooling set point. So if people don't feel comfortable, they can go adjust the set point down and achieve better comfort with a few drawbacks. So we've got increased cooling energy use for reducing the set point, which we showed. There's also the potential to become uncomfortable due to how cold the indoor air has to be in order to control the humidity. And also running at lower indoor set points increases the risk of condensation and moisture durability issues in the building envelope due to condensation. And finally, looking at the equipment, the results showed that reducing the supply airflow rate and eliminating the cooling blower off delay, those had significant impacts on reducing indoor humidity with small impacts on cooling energy use. So those two equipment setup items can be used to help mitigate high humidity in homes and can compensate for oversized equipment that results in high humidity. And these two items are typically easy to adjust inside the air handler with either motor speed taps, diff switches, or jumpers. And moving on to future work, one of the things we really struggled with was choosing a metric for assessing comfort based on both temperature and humidity. We really only focused in on humidity on this, but I think that's a need if we want to try and compare comfort for different home constructions, comparing comfort from different field measurements in homes. We really don't have a good metric there. We saw that the ASHRAE 55 analytical method, the Fanger method, is pretty insensitive to indoor humidity, which is a challenge when there are pretty high expectations for homeowners on indoor comfort. And going along with that, ideally we want this metric to be able to use to come up with some simple value to represent the annual comfort in a home. So as John mentioned, we didn't have any weighting on the magnitude of the humidity excursion or the duration. I guess we captured duration, but there's likely some combination effects there that should probably be considered when trying to distill all these hourly measurements down into a single kind of comfort metric. And with that, we're going to open it up for additional questions.
Okay, great. Thank you so much, Jeff. Thanks, John, and thanks, Jason. This is our question and answer session. So if you haven't done so already, feel free to enter a question into the questions pane. We'll get through as many as we can today. So the first one for our experts today, eliminating blower-off delay seems like easy, high-impact measure to reduce humidity excursions. Is there any downside to doing this? Can most systems be configured this way in the field? Would it make sense for manufacturers to change the default setting? Who would like to answer that question?
I can take that. So we didn't see any downside. I think the only climates where you would see a downside would be in dry climates, where if you don't run with that blower off delay, you're going to lose some of your cooling you've done from ductwork that's in unconditioned space. So that's a fairly limited subset. The blower off delay does provide an efficiency gain per the test procedure, which is why it's used by most manufacturers, but it is typically adjustable within the air handler. So that is something that is an easy change that could be done during equipment setup.
Okay, great. Thanks, Jeff. There's another question that's related to that, so you feel free to expand if you'd like, but they're referring to the graph on slide 62, and they said the slide on 62 is compelling. Is there a scenario where having the blower-off delay engaged is a good thing?
Yeah, so like I said, I think the only situation where you would want the blower off delay is if you're in a dry climate and you've got ducts in the unconditioned space and you're trying to make sure you extract some cooling from that thermal mass that you've got in the unconditioned space that would be lost otherwise if you weren't running with that blower off delay. So in humid climates, I would say probably not. In a dry climate with ducts in the unconditioned space, that there could be some small efficiency gains for using the blower off delay.
Okay, great. Thank you, Jeff. The next question is, how much would the results change if you didn't fix the indoor humidity at 55%, particularly the ventilation impacts? A home that has floating indoor humidity has a lot more times when ventilation is either not a load or a much reduced load and significantly different ventilation impacts.
Right, so sorry if we weren't clear there. So there were different aspects of the study, and in the first part, the first results section that we talked about, where we're talking about sensible and latent loads, that was the only portion of the analysis where we controlled the RH to 55%. In all the other results that we showed, hours above 15.7 degrees C dew point, those simulations did not have a dehumidifier, and so that humidity, the humidity in those simulations was floating. It wasn't fixed to 55% RH. But if we want to look at what the actual latent load is, this was best done by controlling the RH so that we could take a delta between the, so that the indoor humidity ratio is fixed.
Great, thank you, John. The next question is, what is your best engineering judgment on the effect of using variable speed and VRF equipment? Who would like to take that question?
So I'll throw in my 2 cents and say that it depends, which is maybe a cop-out answer, but the performance of variable speed and VRF equipment is so dependent on the manufacturer's controls of the equipment, how they control the blower airflow rate, how they adjust compressor speed. It's really difficult to make overall generic statements about how those systems are going to affect humidity and how their efficiency is going to vary. So my opinion is you can't make a blanket statement on that. John,
okay.
do you have any other opinion?
Do you have anything else to add, John or Jason?
No, I think I think Jeff's answer is correct. Is that I think variable speed equipment does have the potential to help reduce some of the humidity, but it really does matter how it's controlled and how much overcooling would be tolerated by the occupants.
Okay, great, thank you. The next question is, in new construction, does it make sense to choose construction materials of the home to increase or decrease humidity buffering to manipulate the humidity without changing the cooling system?
Okay, so I brought up this one back to slide 52 to kind of help answer that question. I think maybe the answer is still it depends, but our metric was hours above a certain threshold. And so if you use our metric by itself, then there are cases where additional moisture buffering actually makes the problem worse. Although it depends on how you look at this bottom graph here to say, is it more uncomfortable to have this period here where you're much above the set point, and even though you're compensated slightly by being much drier in this region. So I think it really depends on how you define the comfort metric, and I think there's a lot needed there to really understand better. But I certainly think it has the potential, you know, introducing materials that can buffer humidity certainly have the potential to help with high humidity problems.
Great, thank you, Jason. I think the next question is for you, Jeff, because it's another one related to something else that you talked about. But the question is, when did the blower off delay modeling when you did the blower off delay modeling, did you assume that the moisture off of the evap coil begins to evaporate as soon as the compressor turns off?
That's a good question. I believe that the latent degradation model we used assumes that. I'm not 100% certain, though. It's been a while since I've looked at it. But I think that is the correct assumption, and that any moisture that was evaporated had the same amount of sensible cooling associated with it.
Okay, great. Thank you so much, Jeff. With that, since we only have a couple minutes left, I'm going to go ahead and wrap up. And if we didn't get to your question today, we'll definitely reach out to you after the webinar today. Because there have been a few questions about it, as I mentioned at the beginning, we will be posting a PDF version of the slides on the Building America website. And so they will be up by the end of this week, and then it'll take a couple weeks for the audio recording to be up as well. So if you have any questions, feel free to reach out to us. And if you haven't already done so, feel free to sign up for the Building America newsletter so that you can get the latest information not only on webinars, but other resources like publications and things like that. So with that, we appreciate your time, and I want to make sure that thanks to our experts again. Thank you, Jeff, John, and Jason for your time today. And if you do have any questions, feel free to reach out to us, whether at the Building America website or through our Building America email, which is building.america@ee.doe.gov. So thank you for everyone's time today, and have a great week.